Welcome students. In the series of lecture, we are going to discuss about the important concepts for GATE exam. I am going to take the symmetrical component and faults for you. Let us discuss faults first. In the traditional power system, we will have load and we will have a source. Our objective is to supply the energy from the source to the load. To do this, we will use conductors. And in a single phase, for example, in a single phase system, one conductor will function as a go conductor, the other conductor will function as a return conductor, because any electrical circuit should be closed in nature. As I have mentioned, one conductor will carry current from source to load, the other return conductor will take the current back to the source because it is a closed circuit. In the normal condition, the load impedance will resist the flow of current, and in between conductor we will have the insulation which is preventing the current from leaking from the go conductor to the return conductor, or from the high potential to the low potential. If any breach in the insulation happens, the current will be diverted through the least opposition path, which is actually our short circuit, and will not flow through the load because it offers relatively high opposition to the current flow, whereas the breach in the insulation, it may be a breach in the air insulation or our insulation over the wires. If there is a breach in the insulation, the current will be diverted through that path. In this condition, the only Thevenin impedance in the circuit is responsible for limiting the current. So since the Thevenin impedance is low in nature, the resulting current will be high in nature. Because if you see, once the insulation is getting breached, the effective load impedance from the network is removed. Current will follow through the least opposition path. So the resulting current will be high in nature, which should be avoided. These high currents will cause overheating to the source and conductors, which should be avoided. So these kind of faults will happen in our three-phase power system, and we can classify these faults as follows. The first classification is triple line to ground fault, meaning all the three phases R, Y, B will be shorted together and it will get connected to the ground. That is called triple line to ground fault. Then triple line fault, which does not involve the ground. R, Y and B will get shorted together. It is also a fault. Then you have the possibility of only one phase. For example, this B phase is getting short circuited to the ground. Line to line fault. Any two phases like yellow and blue may get short circuited together. Those are called line to line fault. It may be a red yellow or blue red. Anything is possible. Then double line to ground fault. Any two phases are getting short circuited together. They are also getting short circuited to the ground. Like R and Y short circuited, and they are getting short circuited to the ground. Or yellow and blue getting short circuited. Together they are getting the ground. Or R and blue is getting short circuited and together they are getting the ground. Those kind of faults are called double line to ground fault. So this entire faults can be classified into two categories. One is balanced fault. Balanced means all the three phases should be incorporated. There are two kinds. Triple line to ground, because triple line to ground involves all the three phases and it is getting short circuited to the ground. So that is a balanced fault. And triple line fault, RYB getting short circuited together. Since it involves all the three phases, it can be called as a triple line balanced fault. In the balanced condition, since all the three phases are involved, since they are balanced in nature, we can use the per phase analysis to find out the response in the circuit. Whereas when you have when you haven't have all the three phases in the process, it will create unequal current flow in individual phase, which will not possible to use the per phase analysis. You need to do the 3-phase analysis, which is very tough. So we will do the symmetrical component transformation, which takes in the unbalanced conditions in the system, transform into balanced condition of 3 different systems. So positive sequence, negative sequence, zero sequence we will call. So in each sequence the system will be balanced. So we can analyze using per phase analysis in sequence domain. Then we can combine the responses to get back to the original unbalanced condition. This is what the theory behind the sequence components. Let us solve one gate question in this regard. So here the question is, identify the type of fault. The sequence components of the fault currents are given as follows. I positive is 1.5 per unit. I negative is minus j.5. I 0 is minus j1 per unit. The type of the fault in the system is dash. Before solving this problem, we need to understand something. The system is expressed in terms of positive, negative, zero sequence components with respect to the R phase. Right? With respect to the R phase, let us assume that. And we know that from the sequence component theory, any phase component like IR can be synthesized from its sequence component. Here IR positive plus IR negative plus IR 0 can be added together to give the original IR phasor. It is true for IY and IB also. If you add corresponding sequence components, you will have that phase component here. Okay, one more thing. When a fault involves a ground, then it will be reflected as a non-zero value in the zero sequence component. If a fault involves a ground, then it will be reflected as a non-zero component in the zero sequence. If zero sequence component is present, you can confidently tell that the fault involves the ground. If it is the zero sequence component is absent, the fault does not involve the ground. So that is the idea. Let us examine the options one by one. Here first option D. Here you have triple line to ground fault. But triple line means all the 3 phases are involved. Then the fault become balanced in nature. For a balanced system, only positive sequence components exist. No negative and zero sequence component will be present, irrespective of the presence of ground. So here, if it is a triple line to ground fault, then you should see a zero sequence component, a zero negative sequence component. This is not the case here. So option D is ruled out. For a balanced fault, only positive sequence component exists. So option D is ruled out. Let us go to option B, double line fault. If it is a double line fault, because the ground is not involved here, you should see a zero sequence component, which is not the case here. The zero sequence component is present. So option B is also ruled out. Only we have option A and option C. Let us explore option A. If it is the single line to ground fault, then all the currents, let us assume the fault is happening in the R phase, all the R phase current is flowing through the ground. So positive, negative and zero sequence component will be equal in nature. That is the property of single phase to ground fault. Here it is not the case. The positive sequence current, negative zero sequence component are not equal in nature. So the option A is also ruled out. The only remaining option, double line to ground fault, where you will have the positive sequence component is equal to sum of the negative and zero sequence component. That is the property of double line to ground fault. Here you can verify I positive sequence is J1.5, I negative sequence minus J.5, I zero sequence minus 1. If you add the negative and zero sequence component, it gives minus 1.5. So which is exactly satisfying the relationship where the positive sequence component of the current is equal to minus 1 times negative plus 0 sequence component. So in this problem, for this data, it should be a double line to ground fault. Thank you.